Hi everyone. In this lesson we're going to discuss power series. Now a power series is an important concept because, as we'll see, it leads us right into the discussion of Taylor series. In fact, a Taylor series is just a special type of power series. And Taylor series are very important in mathematics because a Taylor series allows us to write very common functions like exponential functions, logarithmic functions, trigonometric functions as a series of polynomials. And polynomials are very easy to calculate. So, as you can imagine, Taylor series is a very important concept in mathematics. So let's start out with our definition for a power series. So a power series in the powers of x minus a, where a is a fixed constant, is an expression of this form. So it's the series of Cn times x minus a to the nth power, where the C sub n is a given sequence and a is a fixed constant. Now if you wrote out what this series looks like, it's going to look like this right here. So you see you have C sub 0, x minus a to the 0 power, so that's just going to be 1, so you just have C0, plus C1, x minus a to the first power, plus C2 x minus a squared, plus C3 x minus a cubed, and so on. So that's what a power series looks like. And keep in mind that the Cn's, that's going to be a given sequence, the a is a fixed constant, and we're thinking of the x as being a variable. So the x is allowed to vary in a power series. And of course, as you put different values for x into your series, you're going to get out different values for the series. So this is really a function of x. Now here's a few examples of some common power series. Let's take a look at this one first. So we have here the summation x to the n divided by n factorial. Okay, let me just write that out here. It's a little bit small. It's x to the nth power divided by n factorial from 0 to infinity. Now if you were to write out what this looks like, put in 0 for n, 1 for n, 2 for n, and so on, this is what you would get right here. So if we put 0 in for n, we get back 1. X to the 0 is 1. Divided by the 0 factorial. 0 factorial by convention is 1, remember that. So you get 1. So this is when n is 0. If you put 1 in for n, you get x to the first power divided by 1 factorial. So you just get x, so that's when n is 1. If you put 2 in for n, x squared over 2 factorial, or just 2, so this is when n is 2. N is 3, you get x cubed over 3 factorial, or 6. And so on. So you see this is the power series that you're forming, and in this case the a is 0. Okay, so you just have x minus 0 to various powers, so the a is 0 in this case, as we state right here. Also notice that the Cn terms, if we're looking back here trying to match things up, the Cn terms down here are the 1 over n factorial. Okay, so keep that in mind also. Now it's a fact, as we'll see when we study Taylor series, and this is very interesting, that this series is actually equal to the exponential function e to the x. So if you put, for example, 2 in for the x, and you calculated out this series, did 1,000 terms or so, added up 1,000 terms of this series, you would get a value that is very close to e squared, or e to any power you put in here. Okay, so that's a very interesting fact, and that's actually a Taylor series. So we'll look at that in more detail in the next section and prove this result. Now here's another example of a power series. So here we have the summation, -1 to the n plus 1 times x minus 1 to the nth power over n. So let me just put that up here. Okay, that's another example of a power series. In this case, the A is equal to 1. That's the point about which you are expanding your power series. And the CNs, those are the -1 to the n. This should be an n plus 1 right there. Sorry, right there. That's an n plus 1. See, down here we have an n plus 1 in the exponent. The CNs then are -1 to the n plus 1 over n. Okay. And if you wrote out a few terms here, n equals 1, n equals 2, n equals 3, and so on, this is what you would generate right here. So you would generate this series. Notice you do have an alternating sign pattern because of the -1 to the n plus 1 power. And in fact, as we'll see later on, this series right here is actually equal to the natural log of x. Now it's only equal to the natural log of x for x between 2 and 0. Okay, so that's a fact that we'll actually consider later on in a few minutes when we look at radius of convergence for power series. This particular power series here has a radius of convergence which is equal to 1. Notice that the interval 0 to 2, you can think of it like this. Say right here is 1, 2 is out here, 0 is right here. So you notice this distance is 1. That's your radius of convergence for this particular power series. Now, we'll discuss that in more detail, and we'll look at a method of calculating that next. Okay, so there's another example of a power series. Now let's discuss what we mean by radius of convergence for a power series. Now, if we're given a power series like this, it seems natural that we would like to know for what values of x does this series converge and for which values does it diverge. Okay, so what we can do is we can actually use the ratio test to help us answer that question. Now, recall this from the ratio test. If we're given a series like this, recall that this series will converge absolutely if the limit as n goes to infinity of our an plus 1 over an, the absolute values, is less than 1, then we will have convergence. Otherwise, if this limit is larger than 1, then we will have divergence, right? And if it's equal to 1, then the test fails. Okay, so recall that is our ratio test, okay? So, to determine the values of x for which this will converge and diverge, what we're going to do is this. Let's first of all consider the limit of these terms, the Cn terms. Well, in particular, let's consider the limit as n goes to infinity of c sub n plus 1 divided by c sub n. Just suppose for the time being that that is the number r. Okay, suppose that's equal to r. Now, to determine the x values for which this converges, we apply the ratio test. So you see right here, we have this. This is actually what we have right here. Okay, you see we take the limit, we take this whole thing here, all of this, we put n plus 1 in for the n's, so that's in the numerator. That's just like the a sub n plus 1 over here. And then we take Cn times x minus a to the nth power, that goes in the denominator right here, and you see we take the absolute values of it. So What we have right here in this limit is exactly this. So we are applying the ratio test to this series. Okay, now we simplify it a little bit. Notice x minus a to the n plus 1 over x minus a to the nth power. That is just x minus a to the first power. Okay, so that simplifies. Now, this doesn't depend on n at all. And as we set up here, just suppose for the moment that this quantity right here is converging to little r, some number, call it little r. Okay, so then what we have here is that this limit is equal to r times x minus a. All right, so you see from the ratio test then we know that this series will converge absolutely when this quantity is less than 1. You see, that's this part right here. Okay? So this series will converge absolutely as long as this condition holds. So in other words, that's what we have right here. This series will converge absolutely when x minus a is less than 1 over r. So this we can write as an interval like this. Okay, so we can write it like that. So we know for a fact that this series will converge absolutely for x in this interval. Okay, now if this is equal to 1, suppose this equals 1, then the test fails, right? So what you have to do then is to determine if you have convergence or divergence at these endpoints, you must put these values in for x and test the series in each case individually. Now it's also a fact from the ratio test that if this quantity right here is bigger than 1, so in other words x minus a is larger than 1 over r, then the series will actually diverge, and that also comes from the ratio test. Okay, so what we can conclude now is that if you're given a power series like this, and you know that the limit as n goes to infinity of the Cn plus 1 over Cn in absolute value is equal to some number r, then your interval of convergence will look like one of these. It'll either look like the open interval from a minus 1 over r to a plus 1 over r with open parentheses there. The open parentheses means that your power series diverges when x equals those two numbers, or for x equal to the endpoints of your interval. Or your interval of convergence could look like this, where you have a closed bracket on one side. That means that your power series converges when x is equal to that number, and diverges when x is equal to this number, and converges absolutely for x in between those two numbers. Okay. Or your interval of convergence could look like this, where your series converges for x equal to this number, diverges for x equal to this number, and converges for all x in between those two numbers. Actually, it would converge absolutely. Or your interval of convergence could look like this, where your series, your power series, converges for x equal to both of the endpoints, and then it also converges absolutely for x in between these two numbers. So there you go. That's how you can determine the values of x for which your power series will converge or diverge. And let's note one other thing in our discussion. If that little r turns out to be 0, so if this limit is equal to 0, then our interval of convergence is actually all the real numbers. You see, because if this little r turns out to be 0 here, then this will certainly hold for any number x that we put in here, because the left-hand side would always be 0. So in that case, our interval of convergence would be negative infinity to positive infinity. And another way to see that is if you look at our interval of convergence right here, or one of these, it doesn't matter. Notice that if the little r is approaching 0, and it would be approaching 0 from the right, then this quantity and this quantity would both be approaching positive infinity, right? Remember how you think of 1 over a very, very small number as being a very, very large number. And so a plus infinity would be infinity, and a minus infinity would be negative infinity. So you see, your series would actually converge absolutely for all x in that case, if that little r turns out to be 0. On the other hand, if that little r turns out to be infinity, well, in that case then, you see, we think of 1 over infinity in each of these cases as being 0 and 0. And so you see your interval of convergence would only be when x equals a. That's the only time your series would converge, is when x is equal to a, right? Okay, so those are two important things to note. Now, in the next theorem, you'll see that the radius of convergence for a power series is actually defined like this. The r in the next theorem is called capital R, is actually defined to be the limit That's what we define the radius of convergence for a power series to be. You'll notice that that's the reciprocal of this quantity up here. You see, we just flip the numerator and denominator. So this is actually equal to 1 over little r, right? And so then our interval of convergence would look like a minus capital R to a plus capital R. And then you'd either have open or close brackets on either side here. Okay, so just take note of that for the next theorem, that this is how we actually define the radius of convergence. And that makes sense because, after all, this quantity right here would then just be capital R, right? So your radius of convergence would be capital R, because if you were to graph this on the number line, here would be A, right here would be A plus capital R, right here would be A minus capital R, and so you see these distances right here are capital R. Now let's take a look at this theorem. Now here's a statement of our theorem that's motivated by our previous discussion. If we're given a power series like this, and we let R be the limit as n goes to infinity of Cn divided by C sub n plus 1, or if we had used the root test, then R would be defined as the limit as n goes to infinity of 1 over the nth root of Cn. Notice that this quantity right here is 1 over the nth root of the absolute value of Cn. This is what R would be if in our previous discussion we had developed our interval of convergence using the nth root test. Okay, then we have the following three cases. If the R exists and it does not equal 0, then the power series will converge absolutely for absolute value x minus a less than r. Or in other words, let's put a number line over here to illustrate this. If this is a, say right here would be a plus r, and over here would be a minus r. Now this is the same as the interval from a minus r to a plus r. So in here, you would have absolute convergence. Okay, so for any x you pick in here, your power series will converge absolutely. Your power series will diverge for the absolute value x minus a greater than r. In other words, out here, all the way to infinity, you will have divergence of your power series, and back here also divergence. And then the series may or may not converge when the absolute value x minus a equals r. In other words, when x is equal to the two endpoints a plus r and a minus r. So in other words, at these two endpoints right here and here, you may or may not have convergence. You need to test those 2 points individually. Okay, so that's what happens if the r exists. On the other hand, if the r is equal to 0, now that also means r exists, but this is a special case here. If the r is equal to 0, then the series will diverge for every x except when x is equal to a. If you put a in here for x, you get 0 back. Okay, so if the r is equal to 0, notice that these 2 points would converge down towards a, so your interval of convergence would be disappearing except for when x equals a. And then finally, if r is equal to infinity, the power series converges for all x. If r is infinity, of course, this point right here would be going towards infinity. This point here would be going towards negative infinity. And so you would have absolute convergence for your power series for every single real number x. Okay, so that's the statement of the theorem, and that was motivated by our previous discussion. Now let's take a look at a few examples. Now in our first example here, we want to determine the interval of convergence for this power series. So the sum of 3 to the nth power divided by n times x minus 1 to the nth power. Now in this series, we identify the c sub n as equaling 3 to the n over n. And also notice that in this case the a is 1. Now thinking back to the previous theorem, we need to evaluate the limit as n goes to infinity of the absolute value of Cn over Cn plus 1. So in this case, these terms are going to be 3 to the n over n. See, that's the Cn. And then in the denominator, we have our Cn plus 1. We just replace the n's here with n plus 1. Now we need to evaluate this limit. Well, just filling in a few details here, notice that this is equal to and simplifying this a little bit, these 3 to the n's will cancel, leaving us with this. And of course, as n goes to infinity, this term right here approaches 1. And so we're left with our answer of 1/3. And so that's what capital R is equal to. All right, so that's our radius of convergence, 1/3. And now what we do is set the absolute value of x minus 1 to be less than 1/3. Notice that's our R. This is going to be the interval on which the series converges absolutely. Okay, now we need to test the endpoints. Let's also note that you can write that series like this. So x is larger than 2/3, less than 4/3. Once again, notice that you get that by simply taking this interval and simply writing it like this, and then adding 1 to both sides, right? 1 plus 1/3 is 4/3, and 1 minus 1/3 is 2/3. Okay, so that's how you get this. So in this interval, you have absolute convergence. Let's maybe draw a little picture up here so we keep track what's going on. Okay, so we have right here, say that's 2/3. Say this is 4/3, and 1 would be right in the middle there. And so in this interval right here, we have absolute convergence. We'll just say absolute like that. Okay. Now we also know that out here then, we will have divergence of the power series for any x we pick out here, and for any x we pick out here, we will also have divergence. Now we need to determine what happens at those two endpoints. So we need to take 2/3 and 4/3, plug them in for x in here, and see if we get convergence or divergence. Okay, so that's exactly what we're doing down here. So first of all, at the left-hand endpoint, when x is 2/3, if we put 2/3 in for this x right here, notice that this quantity, 2/3 minus 1, that's going to be negative 1/3. Okay, so that's what we get right here. And now simplifying this a little bit, just notice that this right here we can write as 3 to the n over n times negative 1 to the n over 3 to the n. And of course these 3 to the n's cancel. And you're left with negative 1 to the n over n. So this is what you're left with right here. Okay, so that's what we're left with when x equals 2/3. Now you notice that this series converges by the alternating series test. We've seen that before. So this does converge by the alternating series test. Okay, so we do have convergence right here at that endpoint. Now let's test the other endpoint when x equals 4/3. So if we plug 4/3 in for the x right here, notice that we get 4/3 minus 1, that's just 1/3. Okay, so what we get then is this down here. So you see we get 3 to the n over n times 1/3 to the n. Now you notice that you can simplify this as, let's see, we have 3 to the n over n times, and this is just going to be 1 over 3 to the n. So those 3 to the n's cancel, and you're left with the sum of 1 over n. Now this we know diverges. And that's by the p-series test or the integral test. We have different tests that tell us that that diverges. And so now we know that at the right-hand endpoint we actually have divergence. So let's just mark that up here. So we know at that endpoint right there we have convergence. At this endpoint right here we have divergence. And so therefore our interval of convergence is going to look like this. It's going to be 2/3 to 4/3, open bracket at the 4/3 because at 4/3 our series diverges, close bracket at the 2/3 because if we put 2/3 in for x we do get convergence, and so this is our interval of convergence, and that completes our problem. Let's take a look at another example. Now here we want to determine the interval of convergence for this series. So the summation of x minus 1 to the nth power divided by n factorial. So looking at this series, we identify that the Cn terms are the 1 over n factorial. So these are the C sub n sequence. Okay, so thinking back to our convergence theorem then, we need to evaluate this limit right here. Now once again, that's the limit. Right? That's the limit of the Cn over C sub n plus 1 terms. Cn is 1 over n factorial. C sub n plus 1 is 1 over n plus 1 factorial. Now flipping the denominator up, you get this. And of course, n plus 1 factorial over n factorial is just n plus 1. Okay, keep in mind once again, right? You can write n plus 1 factorial like this. It's 1 times 2 times 3 up to times n, so that's n factorial, times the last term, which is n plus 1. You see these n factorials cancel, and you're left with n plus 1. Now, of course, the limit as n goes to infinity of this is infinity. And so our radius of convergence is infinity, and so that means that our interval of convergence would be all the real numbers, or negative infinity to positive infinity. Let's take a look at this example down here now. Now in this example, we want to calculate the interval of convergence for this power series. Now take note, for this power series, the exponent is 2 times n, as compared to just n for previous examples we had worked with. Now if you write out a few terms of this power series, this is what it will look like. Now notice that all the exponents that go along with the x minus 1 are even. And that's because, of course, if you put 1 in for n here, you get 2. Then you put 2 in for n, you get 4. 3 in for n, you get 6. 4 for n is 8, and so on. So this is the power series that is generated by this series. Okay, so we want to calculate the interval of convergence. Well, since this power series doesn't exactly fit this form that we've been working with, we can't directly apply the radius of convergence theorem. Remember, that theorem told us that our radius of convergence R was the limit of this quantity, right? Where the CNs would be these terms right here. Okay, so since it doesn't exactly fit this form, we can't use this result. So what we're going to have to do is go back to the ratio test. Now we have the ratio test stated right up here. Just recall what it states. It says that if you're given a series, now this wasn't a power series, it was just a regular series, and you calculate the limit as n goes to infinity, absolute value a sub n plus 1 over a sub n, and you get the number rho back. Then you have these three cases. If this rho is less than 1, that's case 1, then the series converges absolutely, meaning that this series converges along with the series of the absolute value of the an terms. That also converges. Otherwise, if the rho is larger than 1, you have divergence. And if the rho is equal to 1, then the test fails. Okay, so recall that that is our ratio test. So what we're going to do to determine the interval of convergence for this power series is we're going to apply the ratio test up here. We're going to calculate this quantity right here, and then we're going to set it less than 1 and determine what values of x make this less than 1, and that will be our interval of convergence. If you recall, that's actually how we developed this formula here for the radius of convergence R, is by starting with the ratio test. So we're just going to go back and directly apply the ratio test to this problem. Okay, so that's exactly what we're doing right here. Let's just scroll down a little bit. So right here in this line, we are evaluating where the ANs are everything that I have blocked off right here. Okay, so that's our AN. So notice that if we put n plus 1 in for these n's, that's the numerator right here. So right here is AN plus 1. And then AN is the denominator right here. Okay, so this is AN plus 1 over AN. Now we need to simplify this, evaluate it, and then set it less than 1, and we will get our interval of convergence. Okay, so simplifying this, notice that this exponent right here simplifies as 2n plus 2, of course. And then in the denominator, you have x minus 1 to the 2n right there. So notice that these 2n's will then cancel, leaving you x minus 1 squared. Now, these terms right here, you can flip this 2 to the n over n upward and multiply it against the 2 to the n plus 1 over n plus 1. And that's what we have right here. Okay. Now, of course, you have right here 2 to the n times 2. So the 2 to the n's will cancel here, leaving you with just a single 2. Right there it is. And then you have n over n plus 1. Okay, so just simplifying that, we get this right here. Okay, so we get that line. Now, of course, as n goes to infinity, this quantity right here will converge to 1. Okay, so we get our answer, 2 times the absolute value of x minus 1 squared. Technically, you don't need those absolute values because you're squaring it, but they just sort of carried down. All right, now what we need to do is simply set this less than 1 and determine what x values make this true. Okay, so that's what we have right here. And now simplifying this, just divide the 2 underneath the 1. Take the square root of each side to get rid of that 2, and you end up with this right here. Okay, now simplifying that, that gives us this interval right here. Just to fill in a few details here, this inequality simplifies like this, recall. Right, that's how you simplify an inequality like that with an absolute value. And then just adding 1 to everything, of course, we get like that. And of course, this is equivalent to just stating that x is in this interval right here. Okay, so that's how we got that interval. Okay, so we know now that this series will converge for x in this interval. But now recall that the ratio test fails when this quantity is equal to 1. Okay, so this quantity that we calculated right here, okay, this will equal 1 when x is either this number, this endpoint, or when x is equal to this endpoint right here. So we need to test these 2 points individually. Okay, and then that'll determine if, for this interval that we have so far, whether or not we should put closed brackets here, or at both locations. Okay, so if we plug these numbers into the power series and we get convergence, then we need to put closed brackets around one or both of those endpoints. So let's see, that's exactly what we're doing right here now. So if x is equal to the right-hand endpoint, we plug that in for the x right here, or as we have down here, we put it in for this x right here. Now you notice then that the ones here will cancel, and you end up with the summation of 2 to the n over n times 1 over root 2 to the 2n power. Now this part right here simplifies as 1 over 2 to the n power. Just to fill in the details there, just take note that by rules of exponents we can write this as and then 1/2 times 2n is just going to give us n, and 1 to the 2n of course is just 1. So that's how we get this right here. And then of course these 2n's cancel, and we end up with this summation. Now we know that this diverges by either the p-series test or the integral test. That's our harmonic series. We know that that diverges. And so therefore, if we go back to our interval of convergence here, that tells us that we must leave this as an open parenthesis right there. Since the power series does not converge at the endpoint, we can't put a closed bracket there. Now what we have to do is just test the other endpoint, and that's what we do down here a little further. Let's just scroll down there. So at the other endpoint, the left-hand endpoint, when x equals 1 minus 1 over root 2, if we plug that in for this x right here, notice that these ones will cancel again, and we will get negative 1 over the square root of 2 raised to the 2n power. And then we have the 2 to the n over n coming over as well. Now this part right here is also going to equal 1 over 2 to the n power. And to see that, just consider this over here. What we would do is just replace this 1 with a negative 1, right? So you just have a negative 1 right there. That would make this a negative 1 right here. But then negative 1 raised to an even power, like 2, 4, 6, that's going to be positive 1. So you still get 1 over 2 to the n. So there we go. Of course, those cancel, and you still get the series 1 over n, which diverges. So therefore, if we look back at our interval of convergence, we must leave this as an open parenthesis also. So now we've determined that this is our interval of convergence, and we're finished. So the original power series will converge for every x in this interval. And that completes this example, and that completes our discussion about power series and intervals of convergence for power series.